Okay, wonderful people, let us try to look at the conservation of momentum. Right, and try to understand exactly what this conservation really means. So we will be looking at an isolated system. So let me just take you through just an analogy of what isolated system might look like. So suppose this is the universe, and the universe consists of the particles. Here are the particles system. So look at this as a universe with particles all scattered on here. Right. So in this universe, we can have three parts. The three parts that we can have, we can say, let this represent the environment. Also, this represent the environment. And let's isolate this as the isolated system. So meaning inside of the universe, we take one piece and we isolate that system. And we want to study what really transpires inside of this isolated system. That's exactly what we do. Now, in science, a system refers to a set of objects and their interaction with others. So this is exactly what a system is. So a system in science is a set of objects and how they interact with one another. These objects can be, for example, we can have a machine, study how the different objects that makes up the machine interact with another. That's a system. We can have the atmosphere and human beings and gravity, and try to check how these things interact with us as human. That's a system. So the universe itself is a system because everybody is locked inside of it, and we are interacting with everything that makes up the system, which is called the universe. So for interest's sake of science interest, we are in this universe, and then we isolate a portion of space that we call an isolated system from the universe, which is the environment in this case. So this is the entire environment, but we isolate a portion space inside of this environment, which is our interest of study. This is exactly what we do. And then from there, we are saying in science, a system refers to a set of objects and their interaction with others. So inside of this isolated system, we can study how a rock, if you throw it down, it comes. If you throw it up, it comes down. If somebody tries to jump, you fall down. Why are these phenomena happening in you inside of an isolated system? A system where there is an interaction between the objects that finds themselves within that sphere of system. It is a small part of the universe that we consider when trying to understand a particular phenomenon or solving a particular problem. So, by just studying that small portion of the universe, we get to understand the entire universe. Because we know that which happens inside of the small interactive interest that we have been able to isolate applies to everything that is outside. So understanding that little universe of interest which we have created enables us to have a vast understanding of the entire universe. Very, very important that we understand this way of approach that science builds up. Right. We are therefore saying the objects are located outside of the system it makes up the universe. Right, so we often need to study limited number of objects at a time. Of course, this is very true, so that we can, at the end of the day, achieve whatever that we want. This limited number of objects is referred to as a system. So a system is a science or us considering only a certain number of objects that we are interested in studying. So we don't consider everything that happens in the universe. We create our own space, which we call an isolated system, where we can interact with a limited number of objects, and then we can begin our study of interest. Okay, that is fine. And therefore they say an external force is a force that originates from the source outside of the system, not from the object and the interactions within the system. So meaning an external force is a force that acts outside of the system, and then it is external. It is not something that is happening inside of the system. It does not have any interact with the system itself, but it surrounds the system and having only the impact outside of the system. This is exactly what an external would mean. Something that is outside of the system, having an impact outside but not on the inside. Because remember, a system is closed. It's our own universe of interest where we are only dealing with a limited number of objects. Right. If there are no external forces acting on the system, or if these external forces are balanced by other external forces, for example, the net force acting on the system is zero, we refer to this system as an isolated system. So an isolated system is a system where the external forces acting on the systems add up to zero. This is very important. So an isolated system is a closed system where the external forces cannot have impact on the system. Therefore, the net resultant force of the external forces acting on the isolated system becomes zero. It is making a lot of sense because remember, external forces cannot have any impact on the system that is isolated, meaning that is closed. So therefore there is no external force that is having any impact inside of the system. So the net resultant force of such forces, which we call external forces, must add up to a zero. Objects within the system do not exert forces on each other. The objects within the system do not exert forces on each other. For example, when they collide with each other, these forces are referred to as internal forces. So the first thing that is very important that we need to note is that the objects within the system do not exert forces on each other. And here, are they speaking about the system that is isolated or no? Because we read that an isolated system is a system where external forces do not have impact inside of it. Therefore, the net force or the resultant force of external forces is zero. That is fine. And therefore, they say the objects within the system, which system? Isolated system, I will assume, do not exert forces on each other. For example, when they collide with each other, there is no one cannot exert or cannot have an impact on the other one. So they do not exert forces on each other. These forces are referred to as internal forces. So internal forces acting on an isolated system of objects in terms of origin, even if these objects can collide with one another, they do not have they cannot exert a force on one another. I don't know if this is making sense. I do not know. But let's continue reading in this. Friction is considered to be an external force when acting on objects in a system. Right. So which system is this? Let's say, for example, an isolated system. In an isolated system, can we have friction acting on that system? If that system is isolated, meaning it's closed. Any external forces that might want to have an impact in the system will always add up to 0. And now if friction is acting in this system, which is not specified here, whether it is isolated or whether it is not, will it have an impact? Friction will only have a 0 impact on the system if it is isolated, because it is an external force. And we said in an isolated system, external forces add up to 0. So friction cannot have an impact on an isolated system. Why? Because it is an external force, and external forces on an isolated system add up to 0. This is very important. Friction is considered to be an external force when acting on objects in a system. And here they are not very specific, they are just saying a system. Remember, the universe is a system. So if friction acts on a system, which is the universe, of course it will have an impact on the objects in this system. Why? Because it is not isolated. Therefore, it will have an impact in that system which is not isolated. For example, the universe. This is because friction reduces the momentum and the energy that moving objects have. Of course, we see this many times. You try and kick a ball, it rolls up for a few seconds and then it comes to a stop. You throw something upwards, it comes down, and then the velocity becomes 0. There are many cases that reveals the truthfulness embedded statement. For a system to be considered as an isolated system, one can make friction small enough so that it has negligible influence on the objects in the system. So this is exactly what we are saying. In terms of friction, if we do not want friction to have an impact in an isolated system, we make it so small that it becomes negligible, almost 0. Because remember, it is an external force. And if it is there in an isolated system, and we want friction to be incorporated in this, it has to be with a 0 magnitude of force. Why? Because it has to be negligible, because this is an isolated system. Friction, being an external force, has to have an impact in an isolated system of 0 Newton. Worthy of note. Now that is fine, and then we can look at collisions and try to see what they say in here. When two bodies are in motion in an isolated system, that is a closed system, that is a system that does not allow any external forces to act or to react in the movement of these objects, they maintain their total momentum if no external forces act on them. Now, we have spoken about momentum quite a lot because we are trying to have tutorials on this. So if the system is isolated, the two bodies maintain their momentum. Momentum is conserved. Something worthy of noting. Right. Why? Because the influence of the external forces acting on the system is 0. Read that once again. When two bodies are in motion in an isolated system, they maintain their total momentum if no external forces act on them. Let me just correct. Let's not say momentum is conserved. Let's just say they maintain their total momentum. So meaning the momentum of A and the momentum of B is maintained. So meaning to maintain simply means you don't go up, you don't go down, you remain the same. You are maintaining this at a constant speed or whatever that needs to transpire. So they are total. So meaning when I add the momentum of A plus of B will always equals to whatever value there was when I measured this 1 minute now and 3 minutes after. I would still get the same result because the momentum is maintained. This is very, very important. That is, when we add up the magnitude and the direction of the momenta of each body in the system at any given time, this is me exactly, the sum is constant. I makeba mlo chwa. Let's continue in this. When object A and B collide, A exerts a force on B, which acts for a short period of time. B exerts an equal but opposite force on A, which acts for the same period of time. Okay, the action-reaction forces are equal in magnitude and opposite in direction because they are heading in opposite directions. Remember, you can only say that if one is moving east and the other in the westerly direction. Therefore, we can talk about this action-reaction pair equal but opposite in direction. Alright, that is fine. Object A and B have undergone a change in momentum as a result of collision. That is fine. They will collide and move in the direction well. And then the force that B exerts on A is equal to the force that A exerts on B, but in the opposite direction. And the time of contact during the collision is the same. Therefore, it brings us to the equation. Now, let us look at the equation of interest. Now, let us look into this. Now, we are therefore saying force being a vector, the force that B exerts on A multiplied by the change in time equals the equal but opposite force that A exerts on B at equal time interval. And what is this? Remember, we are therefore saying, remember what we said. We said F net equals change in momentum over change in time. You remember we introduced this formula where change in momentum equals F net delta T. You see this? Now look what I'm going to do here. We are saying the force as a vector that B exerts on A multiplied time equals equal but opposite force that A exerts on B at equal time interval. I can replace this with this. So I can say the change in momentum A equals opposite but equal momentum B, being factors also. Remember these factors. Now look what is going to happen. Change in momentum A plus change in momentum B is equal to 0. This is very, very important that you understand and you see this. Highly. Now let us read what they say. This means that the decrease of object A's momentum is equals to the increase in object B momentum, or vice versa, or total momentum conserved. Now let us try to make sense of this. This means that the decrease of object A's momentum is equal to the increase in object B's momentum, or vice versa, or the total momentum is conserved. Now let us try to look into this. Now look what is happening here. Right, a decrease in this should result in an increase in that, or an increase in this should result in a decrease in that, so that at the end of the day, when you add those two, you must get 0 as a sign that momentum is conserved. So remember, all this happens in an isolated system where we allow the external forces to have a 0 impact on the system. Very, very important. And then what else are we saying here? If friction is a force that wants to have an impact in this isolated system, we allow friction to be as small, with the possibility of being negligent, almost to 0, so that these objects can continue to move without experiencing any friction in them, so that we can have momentum being there. This is exactly what we say. Now let us look at the principle of conservation of linear momentum. What does it say? The principle of conservation of linear momentum states that the total linear meaning on a straight line, momentum of an isolated closed system remains constant. So the total linear momentum before a collision is equal to the total linear momentum after the collision. And this is very true. So let us try to demonstrate it. Right, the momentum of FA minus the momentum of B. This is very, very important. So what are we saying? Okay, let me just write it. Final momentum of A minus initial momentum A plus final momentum of object B minus initial momentum B is equals to 0. The final momentum of object A minus initial momentum A plus final momentum of B minus initial momentum of B must be to 0. Very, very important. Again, we are saying initial momentum of A plus initial momentum B equals to the final momentum A plus final momentum B. Now look what we have done. We are trying to look at this in terms of initials of A, B, finals of B. Right. We are therefore saying initial momentum A plus initial momentum B equals final of A plus final of B. This is exactly what you take this one to the sides, they become positive. These ones are already positive. Can you see that? Take this and this to that side, they become positive. And on the left hand side, these ones are already positive. I just regrouped here. Nothing. Therefore, I know momentum. This is mass of object A by the initial velocity of A plus, mass of B plus the initial velocity of B equals mass of A plus final velocity of A plus mass of B final velocity of B. I know momentum is mass multiplied by the velocity, and remember we are dealing with a vector in something worthy of. Therefore we are saying total momentum before collision is equals as a vector final total momentum after collision, and this is something worthy of note. Now, with all the theory part that we have dealt with, trying to explain where we have made mistakes, please forgive us, people. Now I'm going to break it here, and I will see you in the next tutorial where we will be applying the principle of conservation linear momentum.